Hello, in this video I'm going to solve the following problem for you. Let p of x be a polynomial of degree 5 such that p of k equals to k over k plus 1 for k equals to 0, 1, 2, 3, 4, and 5. What is p of 6? That would be a good idea if you pause the video at this point and try to solve the problem yourself first. If you do the calculations correctly, the answer that you will get for this problem is 1. P of 6 becomes equal to 1. Okay, so here we have a polynomial of degree 5, p of x, and then I know that p of k is equal to k over k plus 1 if k is 0, 1, 2, 3, 4, and 5. My question is, what is p of 6? Okay? Of course, this in principle is not a hard problem, but if you want to do it the normal way, it is really time consuming. Okay, so because a polynomial of degree 5 is of this type, ax to the power of 5 plus bx to the power of 4, cx to the power of 3, dx to the power of 2, ex, and plus f. Okay, so 1, 2, 3, 4, 5, 6 parameters are unknown for us, but I also have 6 pieces of information. I know what is p of 0. It is 0 over 0 plus 1. I know what is p of 1. It is 1 over 1 plus 1. I know what is p of 2, and etc. 1, 2, 3, 4, 5, 6. 6 pieces of information, 6 unknowns. Using those pieces of information and solving a system consisting of 6 equations and 6 unknowns, I can find A, B, and C, D, and E, and F. After this is found, I replace 6 for x, then I calculate it. So you see that in principle, this problem is not a hard problem. But if you want to do it in that way, it will be very tedious. Even if you have access to a calculator or, for example, an application like GeoGebra, at least you have to start typing your equations there. We will do it at the very end to confirm that another method that I want to solve the problem, you see that they are consistent with one another. If we want to do it a creative way, then I define a polynomial q of x for you in this form. Okay, this is not one of those cases that you immediately can come up with this definition of a new polynomial. You need experience. So take this problem as one example to help you towards this experience gaining, okay? So what I'm doing, I am defining a function for you in the way that you see here on the board. I take my polynomial p of x, whatever it is, of degree 5, I multiply it by x plus 1, and then whatever it happens, I subtract x from it. Definitely, q of x is a new polynomial. Because if this is a polynomial, you multiply it by x plus 1, it remains a polynomial, and if you subtract x from a polynomial, it is still a polynomial. And what the degree of polynomial q of x is of degree 6. Why? Because this was of degree 5, and if I multiply it, which is of degree 1, it increases the degree of polynomial q of x to 6. Okay, but now why this definition should come to mind? Let us see. Let me calculate q of 0. Okay, what happens? This becomes 0 plus 1 times p of 0 minus 0. Okay, but what is p of 0? P of 0 is 0 over 0 plus 1, so p of 0 is 0. P of 0 is 0, so it becomes 0. So q of 0 is 0. But let me choose, for example, let me give you another example. What is q of 1? Q of 1, it means that I have to replace x with 1 everywhere. Yes, so what happens? This becomes 2 times p of 1 minus 1. But what is p of 1? P of 1 is 1 over 1 plus 1, 1 over 2. So this becomes 2 times 1 over 2 minus 1. it becomes 1 minus 1, again 0. So this means the q of x that I have defined in this way has 0 as a root, has 1 also as its root, yes? And then of course, let me just justify that. Let us say that k is k is 2, 3, 4, and 5. Let me do it in one go. Let me calculate q of k for one of these values. So I have to replace every appearance of x with k, so it becomes k plus 1, p of k minus k. But for these values, p of k is given by this expression, so it becomes k plus 1 times k over k plus 1 minus k. Then this k plus 1 and that k plus 1 are gone. It becomes k minus k is again 0. Yes? So, and that was the motivation why I defined my new polynomial in this way, because I wanted to exploit this piece of information in a way that gives rise to a polynomial for which all these numbers are zeros. So now hopefully you see that I have a polynomial of degree 6. Q is a polynomial of degree 6, and then I realized that all these numbers 0, 1, 2, 3, 4, and 5 are all zeros of this polynomial. Okay? A polynomial of degree 6 with given 6 zeros can be viewed in this form. A constant number, a, multiplied by x minus 0, x minus 1, x minus 2, x minus 3, x minus 4, x minus 5. Okay? So, and then of course you don't need to write x minus 0 because that's just x. So if I ask you, do I know my polynomial q of x? I would say that not 100% because still a is missing. But except that one, I know everything about my polynomial. Okay, so I need another piece of information to help me to fine-tune this a. How can I find that? It is very simple. Go back to the definition of q of x, okay, and replace x with minus 1 this time. Okay, so if I calculate q of minus 1, what will happen? This becomes minus 1 plus 1 times p of minus 1 minus minus 1. I replace every appearance of x with minus 1. And then what happens? Do I know p of minus 1? No. This is not given to me. But the good news is that I don't even need it because minus 1 plus 1 is 0. So this becomes just 0. And minus 1 is plus 1. So using this trick, I extracted another piece of information needed for me to fine-tune this last unknown a. So it means that q of x is completely known to me. If qx is completely known to me, then p of x is also completely known to me because I can move x to the other side and then divide by x plus 1. That will be my p of x. Okay, so that was the point. Okay, but I have to use this piece of information. Q of minus 1 is 1. What does it mean? It means that if I go back to my Q of x, replace every x with minus 1, the output is supposed to be 1. So instead of the output 1, I put it here, and instead of that, I put here, and then instead of x, I put minus 1, minus 0, minus 1, minus 1, minus 1, minus 2, minus 1, minus 3, minus 1, minus 4, and minus 1, minus 5. Okay, so let us do it now. This is just simply minus 1. This is minus 2. This is minus 3. This is minus 4, minus 5, and minus 6. And if you multiply them, what happens? It becomes 720. Yes? So the answer becomes this, and then you calculate a, which is 1 over 720. Yes? Okay, now that we have a to be 120, 1 over 720, I put it back here. So I will have my q of x. So q of x is 1 over 720 times x minus 1 times x minus 2, x minus 3, x minus 4, and x minus 5, yes? So this is my q of x. It is supposed to be equal to x plus 1 multiplied by p of x and then minus x. Okay? But look, I'm supposed to look for p of 6. I need p of 6, so it motivates me to replace every x with 6. Okay? If I replace every x with 6, this becomes 6 minus 5, 1. This becomes 2. This becomes 3, 4, and 5, and finally 6. Okay, so I have to multiply these numbers. And if you multiply these numbers, 2 times 3, 6 times 4, 24 times 5, 120 times 6 is 720, and I have 1 over 720. So the left-hand side becomes exactly 1. Okay? But the right-hand side, x should also be replaced with 6 everywhere. So this becomes 7. And then I have p of 6. This should also be replaced by 6. Okay, and then what happens? I move 6 to the other side. It becomes 7 equals to 7 p of 6. And I am looking for p of 6. So I divide everything by 7. And the answer becomes 1. Yes?
Okay, as I told you in the very beginning of this video, I told you that this in principle is not a hard problem because if we want to solve it in a natural way, we can solve a system of 6 equations in 6 unknowns. But I told you that this is very time consuming, and the solution that I presented before this part was actually a very important tool in your hand if you want to work with polynomials. So I will go and choose the cast view. I will not need the graphics view, so let me take this off. And then the first thing that I will do, I introduce my polynomial p of x semicolon equals 2. It means that I am defining something for GeoGebra. So the first one is x to the power of 5, and then I have b x to the power of 4 plus, and then I have c x to the power of 3 and plus d x to the power of 2 plus ex plus f, and then I press enter. So this defines this polynomial for GeoGebra. Then I want to solve a system, so I start typing system, but as you see, one we have is solve list of equations, list of variables, so I choose this one. In order to introduce a list, I have to use curly brackets, then I type my equations. So do you remember the first equation that I have? I know that p of 0 is supposed to be 0. I know that p of 1 is supposed to be 1/2, and I know that p of 2 is supposed to be 2 over 3, and then I know that p of 3 is supposed to be equal 3 over 4, and then I have p of 4 is equal to 4 over 5, and finally I know that p of 5 is equal to 5 over 6. So let me, 5 over 6. 5 over 6. So let me double check. P of 0, 0, P of 1 is 1 over 2, P of 2, P of 3, P of 4, and P of 5. So that's okay. So this is a list of my equations, but I also need a list of my variables. The unknown variables are A, B, C, D, E, and F. And then I come outside and press enter. GeoGebra actually solves the system of equation and provides this to me. Okay, so what I want to do. So I want to do this polynomial. So I would say that let me type p of x again, and then I use this substitution. Okay, so what I will do, I will type those numbers provided by GeoGebra here. So if you see, GeoGebra provided that a is that number, so it's 1 over 720, and then I go read b. As you see, b is minus 1 over 45, so I would write 1 over 45, and then c is 101 over 720, and d is minus 163 over 360 degrees. Yes, and then I have e to be 5 over 6, And then f is 0. If you see it here, it's not that clear. I cannot move this window around, unfortunately, but we know that it's 0. And then what we are supposed to do, we are supposed to replace x with 6. Okay, so I have to replace x with 6, and then I press enter. And as you see, the value of that polynomial for these numbers and x equals to 6 is exactly 1, as we calculated using the other way that I showed you before this part of the video. Of course, this looks a little bit faster because we are using GeoGebra to solve the system of 6 equations in 6 unknowns. Otherwise, the previous method is both more efficient and, of course, deeper. It allows you to understand the deep meaning of zeros of a polynomial. Okay, so at least it is confirmed that this is working.